Okay, a few things about your exam printouts that we just handed back. We have this huge pile to get through, and I only have one TA. In my other class, I only have 0 TAs. So we have to go through it really quickly. So if we ask you to get your self up to the front, it's so that you can get your test within a few seconds, because we have to go through this pile really fast. Now, it's not so if I tell you we already got through your name and you have to get your printout after class, it's not because I'm trying to be a jerkwad or something like that. It's just that we have such a huge thing. We got to go through it really quickly. But hopefully if we dismiss a little bit early today, I'll be able to, catch the rest of you guys. They're a little bit slow on the uptake. All right? So it's no skin off your nose or anything like that. You're not in trouble. But do remember to try to get up here when I ask for your names up here. Okay, comments. You have your printouts. As always, keep those printouts for study guides. I will also, after the noon lecture, I will put the blurb sheets up for you guys. They're already PDF'd and scanned. And I'll put those up on the exam blurbs page. And also, I will unmute your actual Scantron grade. Now, for this exam, it's a little bit different than usual. Usually we have 2 subscores, the Scantron score and then the clicking score. This one we have a bonus item on clicking, and so I'm going to put that in a separate column, and that way you'll know if you got part of the bonus right. I used to be able to print the sentence that you coded in and upload that into web courses, but with Canvas you can't do that. You used to be able to do it on Blackboard pretty easily. It was actually really nice. But you can't do it on, but I can give you the score that you got. And so I'm still in the process of doing it, but your exam 2 clicking, that's 9 points out of your 50, is up. And if you look at your web courses grades page, you'll see that right this minute if you want. Your exam 2 Scantron is in there, but it's muted. And I'll unmute that after the afternoon section, or the afternoon lecture. Then the exam 2 code bonus points, that's 3 points possible on that. That will, I don't know, maybe tomorrow I'll get that. I'm still grading that. I'm still looking at it, so I'm not done grading that one. But your regular 9 points, the first 3 questions are up from clicking. So now a couple reminders to you, and that is that we are going to keep the best 2 out of 3 midterms for your semester grade, but only if you're here for all 3. If you were here for exam 1 and 2, and for some reason you miss exam 3, then exam 3 is the one that's dropped, and you don't have a chance to do better than you did on exam 1 or exam 2. So I highly recommend, if you've made it to exam 1 and exam 2, make it 3 in a row. And that way you will have the luxury of dropping your lowest score. And I looked at the averages and stuff. I'm not done making the averages because we still have a lot of exam bloopers. People messed up their PIDs again, or their PIDs. And a couple people, you know what? I don't know if it was in this. It was in this class. One of the students, I can't remember who it was, they turned in a Scantron that was really crinkled up. And try to come to class with an exam Scantron that's not all crinkled up, because they couldn't run it. If somebody else turned in, I don't even want to ask why, but somebody turned in an exam that was stuck to another exam. So there's some substance that was on there. I don't know if it came out of their nose or what, but it was a little bit disgusting. It didn't get graded. So I'm not looking at anybody, but whoever. But if you didn't get a printout today, it might have been you. I'm not going to ask for a show of hands. But anyways, there was a lot of people that didn't get a Scantron. I got a huge number of printouts here for some student known as unnamed students. And that's what they do when they have a test that has the test form filled in, but they messed up their PID. So if if your PID is 7057057 and you type in 75757 or you bubble in 757, it's not going to be on anybody's roster. They'll grade it, but they won't be able to tell whose it is. I'll be able to tell whose it is, but I have to dig it out of the huge pile of Scantrons that are not alphabetized or anything. So it's a pain in the you-know-what. But we will get it done, and we'll figure out whose exam it belongs to whose. And there's no problem. But if you're the one with the extra crinkled up, I mean, it looked like it was run over by a car. And it was so close to 11:45, I couldn't, and I didn't have an extra Scantron. We have done that in the past, just rebubble it on a fresh Scantron. So it was so close to the end, we couldn't do it. But whoever it was that had the Scantron that was, and you know what else? The person that had the disgusting, I don't even want to describe it, stuff on their Scantron, they messed up somebody else's Scantron that was stacked on top of it. So there's two people that got messed up by that. So try not to sneeze on your Scantron or anything else. Don't drool on your Scantron. This is the first time in a while I've had one that came back ungraded because it was wet. Anyway, now, last reminder for you, now that we're done with that disgusting topic. The last reminder today, exam-wise and so forth, midterm 3, you definitely want to make it, and do not blow it because it is Tuesday. It's not. Now, normally I have Thursday exams. When I'm on a Tuesday, Thursday schedule. And when I'm on Monday, Wednesday, Friday schedule, I have Wednesday exams. But this one I have to have on the 24th, a Tuesday. It's on your syllabus, so there's no surprise about it. But I just want to make sure that you come and try not to be late and stuff. Questions about that? Any exam-related concepts? Yeah. The average, I am not sure yet. It was a little bit higher than last time, but we had so many people with bloopers. There was like about 17 people that don't have Scantrons, or they drooled on the test, or something. So there's a bunch of scores I don't have yet. But I could tell, even if no matter what their scores are, it was a little bit higher than last time. So 70 something, I think. So as I mentioned, things balance out. The first test is usually kind of rocky. So we'll see. Eventually, I'll be able to tell you about it. Another question. Tyler, you got a question back there? Doing good? All right. Tyler, I know it wasn't you that drooled all over your test because you got a Scantron back. Good. By the way, does anybody have an idea of what day my office hours are? Oh, yeah, it does. It does say. Somebody up here in the third row said, Dr. B, it says it right up there. It does. Every day it says it up there. Wednesday, 9 to 12, noon, in room 158 in the Physical Sciences building. The number of people sending me text messages about that is kind of crazy, but. So we'll be having office hours tomorrow. And you know what? We had a ton of people at office hours last Wednesday. It was really, really good. We did, you know what we did last week? For office hours, almost every single minute was taken up with the Tweety Bird Turbo Jam homework problem. And it's good because I made another similar problem like that on the exam, so which I secretly knew I was going to do. And the people that came to office hours got a little bit of extra reinforcement on that, so that's good. Hopefully they scored a little bit higher on their midterm exam too. All right, now speaking of averages, let's take your calculator out and your clicker. Let's do some easy, simple averages. And we're going to be dipping forward into Chapter 5, concepts concerning temperature and heat. A little thermo this week. And believe it or not, the concept of average is part of that. As always, we are on function frequency BB, Bravo, Bravo. So make sure you swap over. Question 1. Why don't you write down this table of data in your notes, just for extra safety. Calculate and select one of the options. Yeah, so hopefully this is pretty basic calculation. You can't write it, you can't really do it in your head, but you should be able to do it easy on paper if you don't have a calculator. But if you have a calculator, it's the minute work of a minute. Nisha, you can take off. Nisha, you can take off anytime. Yeah. One minute. $30 seconds. $15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Let's see what you guys voted for. Wow. You guys are functioning at genius level for the most part. Actually, this works out nice. Yeah, most of you voted for 1503, and 1503 is the correct answer, 15.03. This one, all these things are supposed to be tempting, but I can't remember how I calculated this one. But apparently 21 of you, does that say 21? Wow. And 14 of you chose this. Okay, if that's you guys, here's your basic strategy for averages. Add them up and divide by how many. That's how it works. So this is supposed to be a fairly cinchy one, but what I want to do next, let me get this panel back over here. What I want to do next is another calculation. Hit your refresh key, and you're going to be typing in an answer on this one. You're going to calculate again. Similar kind of thing, but it's a little bit bigger, and I'm going to give you time to calculate it. All right, and so here we go. New data, one speed for every. You know what? That shouldn't say speed. It should say coordinate y. One new y coordinate for every centimeter of x. I'll have to change that for the afternoon class. Anyways, the table is correct. Go by what the table says. Compute the average value of y. And let me turn the light on for you. Making a little light on the subject. That's not too bad. Yeah, this is not bad. Yeah, every semester there's at least a few people from down in the Caribbean somewhere, St. Thomas or Antigua or something. It's not BVI. One of my students from a couple years ago was from Tartola, and she did really great, and she's got a job up in Tallahassee now, so she did really good. I hope you get as good success as she does. She did. Okay, 30 seconds. That should be enough. Are you going down for Christmas? Good. And that's always a good thing. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. Answer is 19.5. Most of you got it. That's good. Somebody over here, well, one person with 195. And you know what? Half the reason I turn the lights on is so you can see that little decimal point. It is really hard to see. So if it was on a test, I would give this particular individual like maybe partial credit, because they obviously blew the decimal point, and the decimal point is hard to see. Now, let me move this out of the way. Get back over here. This table of data, you notice anything about those numbers? You see a pattern? Raise your hand if you see a pattern. What do you see? Yeah, it goes up by odd numbers. Okay, odd numbers on the way up, same odd numbers in the reverse order on the way back down. That is significant. What else do you see? What do you see? Are you sure about that? A parabola? You mean like this? Yeah, it's exactly a parabola. Very good. Yeah, and therefore it is symmetric left and right, except I'm running a little bit past on the right side all the way out to 10. How did you see that? Lovely. That's amazing. I'm amazed that anybody could see that that's a I thought I was going to mystify everybody, but I guess I didn't mystify you. Anyways, here's the parabola, and it's a function. I mean, I just made it apply. Y equals minus x minus 5 quantity squared plus 28, I think, something like that for the formula. And the horizontal, go ahead and sketch that. The horizontal dashed line is the actual average value of y. So if you were to take the average value and measure, and here's the cool thing. If you take the average value and measure the area underneath that, it's a rectangle, it would be very close to the average, to the area underneath the parabola itself. So, it wouldn't be really precise, but it would be in the right ballpark. So it's kind of an interesting thing. Now, I'll talk more about averages on Thursday. For now, I want to talk about something that does involve averages, and that's gases and temperatures. And I love this picture because if you look at this, you'll see that lovely storm off in the distance. All right, that's atmospheric gases and little droplets of water that form the clouds. A cloud is not water vapor. A cloud is droplets of liquid water that are so tiny and light, they're borne aloft on the upwelling warm air rising. And so they stay up there until the droplets, sometimes they combine together and, by random collisions and stuff, and they become a bigger droplet, and eventually they'll be so big they fall. They won't be able to be sustained by that thermal convection, and that's how you get RAIN, rain. Anyways, let's talk about gases and temperature. One of the most amazing theories of the last 300 years after Sir Isaac Newton is called the kinetic theory of gases and the molecular theory in general. And a lot of guys have worked on that over the years. And a gas is a little bit simpler of a substance in some ways than a liquid. And a solid is actually a fairly simple substance because it has really strong, like a diamond has a strong crystal structure. And even something like glass is a pretty strong structure. But gas is considered to be the easiest to tackle, so that's what we're going to tackle. Collection of molecules, and here's some of the properties in the kinetic theory of gases. You've got a huge number of molecules, like 10 to the 23rd power of molecules or more. So if you, for instance, buy one of those little helium balloons at the checkout stand at the grocery store, where it says have a nice day or whatever, happy birthday, that's going to have 10 to the 23rd power or more molecules of helium inside it. Right? So the thing is, though, that they're so small that even though there's that huge number, they're still going to be, on average, really far apart. But they will have a random distribution of speeds. So you'll have some slow ones, and you'll have some fast ones, and you'll have some medium ones. And one of the really cool assumptions about the kinetic theory is really this, that the speeds are distributed randomly. Now, if you think about it, a lot of people say, oh, the universe is random, nothing happens by plan, and, we're just an accident of nature and everything. But, the universe is not random. And a really good way to think about that is, all right, how do you define random? How do you find, random would be the case where everything is the same, and, so you have a box of BBs, they're all the same, and, they go around in a random manner. But the universe is not like that, because electrons are different from protons, and protons are different from neutrons. So, all right, so you can't have, so what if the universe were all neutrons? Well, even that, you can't really have a neutron without having some kind of a structure. A neutron has a structure known as a quark. There's 3 quarks that build up a neutron. All right, so what if the universe was all quarks? Well, the quarks interact. And so it really is true that it's really hard. I mean, it's easy to think about randomness, but actually having something random is not really possible. But in this idealized view, this theory, we think of a gas as being random, and it actually is pretty close to truly random. Okay? The other thing is that they don't really interact with each other than ricocheting off each other when they collide. So a helium molecule, or a hydrogen, if you've got hydrogen gas, or oxygen, O2, 2 atoms of oxygen bound together for oxygen gas. If those molecules bounce off each other, that's about it. Or they might bounce off the walls and kind of ricochet around inside the walls of the container. So this is assuming that you have a sample of a gas in a container. So like a cylinder of, like a scuba tank or something like that. That's compressed air, a couple different kinds of gases in there. Or any kind of tank, or even a balloon would be considered a container. So they're in there, and they don't have any other interaction. So what kind of interactions don't they have? Well, they don't have gravitational interactions. So as a side note here for 1C, make a side note that we don't think of them as being gravitationally attracted to each other, because gravity is so weak. Also, we don't think of them as having long-range electromagnetic. Like repels like, and opposites attract. We think of this kind of idealized gas as not having any of that stuff happening. Right? So when they collide, they bounce off each other like BBs or billiard balls on a pool table, 3-dimensional pool table, billiards flying all over the place. But other than that, nothing. Or the walls of the container. So that's it. And then the fourth assumption in the kinetic theory of gas is, all right, we can't really see these little babies, these little molecules or atoms, but if they really do exist, they better obey Sir Isaac Newton's 3 laws of motion, F equals ma, etc., etc. Right? And based on these four principles, and you can dress them up with a lot of math and calculus and stuff, a couple of really cool things happen. You cannot, and I guess this should maybe be 1E. You cannot track the dynamical state of individual molecules, TJ. There's just too many of them. They're too tiny, there's too many of them, and they're too hard to see. We barely can make out, in this our day, individual molecules. We've just been able to do that in the last 10 years or so. But in the time of Galileo, no. They didn't even think about molecules back then. In the time of Sir Isaac Newton, no. In the time of Michael Faraday, no. They couldn't see molecules. But they were already thinking about them in a kind of an idealized way or a theoretical manner. But they're too tiny to see. So, because they're too tiny to see, you cannot track an individual dynamical state. So, we assume they obey F equals ma, but we can't get a velocity or a position for any single molecule, right? So, single position, so x and velocity, position x and momentum, we can't figure that out on an individual basis. But on an average basis, yes, we can. And that's the key. And that's why we've been talking about averages. Now, you did some really cinchy averages, but the kinetic energies, if you average them in a gas, you get some interesting results. So first of all, in a gas, it's a random distribution, so there's a huge range in speeds. Now, they're all really whipping around pretty fast. Like the gases in this lecture hall are moving at a pretty high rate of speed. Well, they're so tiny you don't really notice them bumping into you, but they're ricocheting off your nose. They're ricocheting off your earlobe. They're ricocheting off your eyeball. They're ricocheting off of everything. But they're so tiny you don't really notice it. But collectively, you can. And so the average kinetic energy, so in other words, just like the parabola that we were looking at, you took an average of the y position. If you take an average of the kinetic energy over and there's a zillion of them, we find that it's proportional to the absolute temperature. Now, underline that word absolute temperature because it's something I have to explain to you. But the average kinetic energy, the way that they can figure that average, you guys had a list of all the positions on that parabola, but we don't have that for a molecular gas. They're too tiny. We don't have a list. But we can use two tools. All right, so that should be 2A and B. Sorry, you guys. So in item 2F, the average kinetic energy and so forth, make a side note to that. The two tools that we implement or that we use to get this result about average kinetic energy are stats, big time, statistics. So any statistics class that you've had, and then multiply that by about 3. And then 2, the second tool from your tool belt, calculus, out the wazoo. A lot of calculus. So statement 2F on the notes here is a verbal English statement that is possible to write down as a true statement because you have used stats and calculus out the wazoo. And you come to that realization that you do these enormous calculations using calculus and stats, and at the end of all that work, you have a very simple relationship that the average kinetic energy is proportional to the temperature. So if you measure the temperature, you're able to immediately say, all right, well, I know the average kinetic energy of the molecules in this gas. I don't know a single molecule's energy, but I know the average. And here's the other thing about this. You can make this as a second side note. The number of molecules with the average kinetic energy is ginormous. It's huge. You know, they're distributed, but the effect is that in a gas, there's going to be many, many molecules that have the average or very close to the average. Okay, so you have really fast ones, you have really slow ones, but you don't have a whole lot of those guys. But you have a huge peak in the number of molecules at the average and near the average. So, now, what is absolute temperature? The Kelvin's temperature scale is the temperature scale we use to measure an absolute temperature. And here's a diagram from another textbook that I won't mention. And it shows Kelvin, Celsius, and Fahrenheit. Now, Celsius and Fahrenheit you already know about, I hope. Okay, they're based on water, what water does. Okay, so Celsius and Fahrenheit, the baseline for those is the freezing point of water. So that's up here. And let me get my cursor over here. Okay, so that's this middle line where water freezes. Okay, 32 on the Fahrenheit scale, 0 on the Celsius. Now Celsius anchors the other end of its scale. You know, you got to have 2 points, you know, if you want to make a scale. Now, so a mile is, you know, point A to point B, 1 mile, 5,280 feet. Same thing here on a temperature scale. The other, for Celsius and Fahrenheit, the other end of the scale is the boiling point of water. And that's kind of what we do in the metric system. You know, a lot of stuff is based on liquid water. And in this case, the freezing point and the boiling point. Now, in the metric system, the Celsius scale, there's 100 Celsius degrees. So they like to have things in multiples of 10. So that's what they decided to do. But now Fahrenheit, Professor von Fahrenheit from Germany, one of those Germans, but notice how many degrees there are between freezing and boiling? 180. That is not a coincidence. It is not a coincidence there's 180. In other words, that's a full turn, or excuse me, that's a half a turn from pointing in one direction to pointing exactly the opposite direction is 180 degrees. All right, so that's kind of what they were thinking about when they set up, or when Professor von Fahrenheit set up his thing. Now, we're not going to be messing around with Fahrenheit or Celsius for that matter a whole lot. Fahrenheit, almost nothing. We'll talk about it a little bit today, and that's it. Celsius, occasionally, you know, like if you look up weather data, a lot of times it'll be in Celsius. But for us, we're going to be working in the Kelvin scale for all our heat calculations. That is the absolute scale. That's this one over here. Now, this one is oriented to absolute zero. You know, we said that the temperature is related to the average kinetic energy. So they said Lord Kelvin, William Thomson, over there in Scotland, said, all right, so if that's proportional to the average kinetic energy, what happens when your average kinetic energy is 0? That should be the absolute lowest possible temperature that you can go. And so he kind of decided, let's use that for our 0 point. And that will be a normal thermodynamic scale going up from absolute 0, no random motions of any kind, you know, higher and higher, acquiring more and more average kinetic energy as you go up. So down here, you're talking about zippity-doo-dah down here at absolute 0 on the Kelvin scale. And up here, you've got plenty of, this is the freezing point of water here. And on the Kelvin scale, it's 273. This absolute zero is minus 273 on the Celsius scale. Now, that's all we're ever going to do. If we have a Celsius temperature, add 273, and you have the Kelvin temperature. We're not going to dibble around with converting Celsius to Fahrenheit. And why is that? Because I consider that to be boring. So we're never going to mess around with, all this 5/9 and 9/5 and subtract 32 or add 30. We're not going to mess with that. But Celsius to Kelvin, yeah, it's 273. Add or subtract. So, and most of the time, I'm going to give you homework and exam questions in the Kelvin scale. And you'll see on Thursday when we start to calculate the changes in the energy state of a substance by temperature, you'll see how the Kelvin temperature scale comes in. Now, this is a good point to make a mention about the textbook. We're now in chapter 5. I was thinking about giving you a free chapter on angular momentum, but I want to push forward. I might give that to you as a parting gift at the end of the semester. We're in chapter 5, and I have already typed in highlighters, highlight notes in the bookshelf application. I highly recommend that you start looking at those. In the next 24, 36 hours, I'm going to be typing in more. So here's your homework for tonight. Read up section 5, up to and including 5.4, and look for my notes. I'll see you on Thursday. You're dismissed. If you didn't get your exam printout, come on up. I'll give it to you now.